Thinking in C, Chapter 2, Fundamental Data Types. What I mean by fundamental data types is numbers, the things that are the basic building blocks of all entities in a program. And those numeric types are integers. Characters are just a special form of integers. You're probably aware of the fact that to deal with characters in a program, you have an underlying character set, which is just a way of encoding each character that you use into some number. So the most commonly used one is ASCII, and an example would be a lowercase a is a 97 in decimal. So characters are really just numbers, but of course they're treated differently in your program. The real numbers we've already talked about are called floating point numbers, and those are the basic types that you have, integers and floating point numbers. Of course, you want to be able to initialize integer and real variables to some value, and so you have to have a way of specifying literals. And that's just writing numerals right in your program. And also defining variables that don't change, which would be constants. Of course, there's also a difference in arithmetic, whether you have integers or real numbers. And it's not just in whether you can store decimal portions of a number. There are some things to watch out for. If you've done any mathematical type programming, you know about round-off error and things like that. We'll just talk briefly about that. And sometimes you actually want to do conversions. You want to take a floating point number and chop off, for example, its decimal part. And you can do that. So we'll show you how. Integers come in different sizes in C, which shouldn't be surprising since it's a systems programming language. And so you have different sizes of integers for different purposes. The most important one being the int, which matches the word size of your machine. And so most machines are 32-bit nowadays or bigger. And so that's the size that an int would be. And the C standard guarantees that an int would be at least 16 bits. So, for example, if you were using compilers under, say, Windows 3.1 or just DOS, you would find that an int would be 16 bits, which means it can store a number up to 32,767. Actually, you've got to think about that for a minute. 16 bits, you would think that it would be 2 to the 16th minus 1, and that's really, well, nobody knows that off the top of their head, but it happens to be 65,535. What's going on? Well, it turns out integers can be signed, and in C they can also be unsigned. Now, we're not going to talk about that in the first 7 chapters, because in Java you only have signed integers, and so that top bit is always used as a sign. We won't talk about that until chapter 8 for the C++ folks. So just keep in mind for now that all integers are signed that we're going to be talking about. And they come in 3 different flavors. Int being the one we've been talking about, but you can also define something to be short or long. You don't have to actually say short int. You can just say short. That's what most people do, and that's okay. And the way this works is that on most platforms, short, int, and long are really not all distinct. I'll have to admit I've never seen a platform where all 3 of them are distinct, although it's certainly possible. The way it works is that on a 16-bit platform, short is usually the same as int, in other words, 16 bits, and a long will be 32. And the opposite is true on a 32-bit platform. An int and a long will be both 32, and a short will remain 16. Again, this just gives you the flexibility to have different sizes of integers. Perhaps you don't need a number with the range of 32 bits, and so you can save yourself some space. As I said earlier, characters are really just integers. How they are stored depends on the encoding that you're using. ASCII being the most common, but there are certainly others. For those of you that have used IBM mainframes, you're familiar with IPSIDIC, which is considerably different than ASCII. There's also a standard, which is a superset of ASCII called ISO 8859, and that's actually in very wide use. It includes some characters that are needed in other countries besides the United States. The current encoding, which is, well, not only becoming more popular, but very important, is called Unicode, which to me, I believe, suggests a universal encoding. And it is a 16-bit encoding as opposed to 8-bit for the other three that we've seen here. The purpose of Unicode is to allow a single encoding for languages throughout the modern business world. Well, we don't have time to go into this, but it turns out that there's lots of different encodings. You can't just use ASCII and go to Japan. I mean, you've got to have an entirely different alphabet. And the same is true throughout the world. You have to change. And so there are so many different encodings, and to write programs that can adapt themselves to different encodings is extremely difficult and has been one of the biggest impediments to programs being made for the international market. So Unicode is an attempt to solve that problem, and it turns out that Unicode is the encoding used in Java. Now, there is no encoding specified for C or C++. It's left open. But for C and C++, the basic character data type is char, or char as some people call it, spelled C-H-A-R, and it's a byte. That's pretty much all there is to it. When you think of a byte, well, that's what a char is. And on every machine I've ever used, a byte has always been 8 bits. So the basic C character does not allow you to use Unicode. It turns out, though, that for this reason they have defined a new type, which is available in both C and C++, called wchar-t, and that stands for wide character. And so sometimes we call the char a narrow character. A wide character is wchar-t. And there are even some functions in the library, although we won't go through them in this course, that will deal with wide characters. And on most systems, a wide character is 16 bits, and so it allows you to use Unicode. But all of this needs to be supported by the compiler and by the platform that you're on. There's an awful lot of ifs there. What we're going to be doing here is just using single characters, that is single 8-bit characters, single bytes, and using chars. You might find it a little disconcerting, or at the very least frustrating, that I haven't really talked about what the range of the numeric types are, because you can't. They're different for different systems, and that can be kind of troublesome. You know, you want to write programs that can run on different systems. You want portability. C is supposed to be a portable language, and to some degree it is. But again, the fact that it is a systems programming language means that in some ways it's more system-friendly than it is programmer-friendly. Now, that's not true to a large degree, but it certainly is true with the underlying numeric types. And so I can't tell you a universal value for the largest integer and the smallest integer. It differs from platform to platform. But you can find it out. You can query it in your program by examining constants that are defined in a couple of key header files that come with your system. For example, the integer limits are defined in limits.h. So if you include that, and if you look up in your documentation what the names of those constants are, some of which I'm going to show you shortly, then you can use those in your program. You can find out what the largest integer, the largest short, the largest long, the smallest as well. So it does give you some programmatic control over the numeric properties of your system. The same thing applies to the floating point numbers as well. And you can get that information from the header float.h. Here's a sample program that illustrates using limits.h for the integral limits. Notice that I include standard I/O, as always, because I'm going to be printing some things out. I'm also including limits.h so I can have access to these constants. You'll notice that constants typically are written with all capital letters. That's a convention that's been around for a long time. I'd suggest that you use it. So if you look at the first printf statement in this program, it's printing out the limits for the char data type. Looking at the format string, it says char and a colon, so that will be printed out literally. And then you come to the %d, so that says print the next integer, which is the next argument in the argument list for printf, as a decimal integer. Then print a comma, and then the next integer, which will be char max, print that out also, and then a closing bracket. So it works the same way for each of those statements, for char, short, int, and long, and you can see the values that come out there on the bottom. And you can see then for this platform that I'm on, it's a 32-bit platform, and so indeed int and long are the same. It's the smallest and largest numbers that you can get with a 32-bit signed integer. And so basically it's 2 to the 31st minus 1 for the max, and minus 2 to the 31st for the min. The floating point types come in several flavors too, float, double, and long double. And the intent is similar to the integers. It allows you to have different sizes. The standard does not say that these really have to be any different. A compiler is at will to make them the same, and so float and double and long double can all be the same precision, the same set of numbers. But that's not really common to have all three of them the same. What is more common is that double and long double are the same. In other words, compiler vendors have not gone to great lengths to come up with a more fine-grained set of floating point numbers and called it long double, which differs from double. The compiler that I'm using for these examples, however, does do that, as you'll see shortly. So the point here is that you have three different precisions. If you've done any numeric programming, you know how important that is. You know that basically the way floating point numbers work is you have a fixed number of digits for your mantissa, for the body of your number, and then a fixed number of digits for your power, and it uses scientific notation. So you can have some pretty big numbers, but you have a fixed number of digits. And so as you do calculations which involve a lot of digits, in other words, a high amount of precision, well, you can lose accuracy. And there's a whole science built around analyzing and controlling that source of error, and that science is called numerical analysis, which mathematicians are familiar with. For our purposes, we just want to note that there are three flavors of real numbers. They may or may not differ in the number of digits they allow, but generally you will find that float is the least precise. It's often called single precision. Double, of course, is double precision, and they're different on most platforms. Long double depends on your vendor. So this sample program illustrates the floating point limits, some of them anyway. You may want to look up in your manual or actually search out the float.h header on your system and actually take a look at it. There's lots of definitions there. I'm just illustrating a few. For example, I'm printing out the radix. The radix is the base that is used for your scientific notation. When we do things by hand, we usually use base 10, but that's not what computers usually use. You'll find that a lot of them use 2. And the output on the next page will actually reveal that on my system, the floating point radix is 2. So basically a floating point number then consists of a certain number of binary digits, and also for its power, or for the exponent, it will also be a certain number of binary digits. In other words, it'll be the mantissa times 2 to some power. Let's see, what's next? Float mant dig. That gives you those number of digits, the size of the base part of the number. For the floating point type, that's what the FLT means there in the beginning. To see how many digits you get in the mantissa of a double, well, then you print out DBL underscore mant underscore dig, and then likewise for long double there. So I'm printing out the radix and also the ranges for the numbers that you can get with the three different floating point types. Here's the output from the program in the previous slide. You can see that on the system I'm using, the base for the floating point system is 2. And so that means that for float, I have 24 binary digits, or 24 bits, in the mantissa for my number. So a floating point number on this system would be 24 bits times 2 to some power, where that power is in some range. The final result of that will be a floating point number in the range of 1.17549 times 10 to the minus 38 to 3.40282 times 10 to the positive 38. So that gives you the idea of the range of what you can have with a float on this system. And double and long double are different. So this is a pretty nice compiler vendor that was kind enough to give me a floating point system with 3 distinct flavors. The double, as you can see, gives you a lot more range, 10 to the 308th, and that's quite an improvement. And long double still it uses 64 bits in the mantissa, but evidently the power has quite a bit more range too, because look what I get. I go from 10 to the minus 4932 to the positive 4932. So the floating point number system you choose really makes a difference on the precision and the range that you get. One feature of floating point numbers, which perhaps is not as widely understood as it should be, is the fact that they're not evenly distributed. Now, if you sit down and think about it, it makes perfect sense. You've got a fixed number of digits in a mantissa, and you can multiply that by some base to some power. Now, as that power increases, then the meaning of each digit increases as well. And so there comes a point where the distance between numbers is quite great because it's being multiplied by a larger and larger power. So the diagram here just shows you a flavor of what that means. It just means that your numbers which are close to 0 are the closest of all your floating point numbers. And then as you move away from 0, your floating point numbers are farther away. There's bigger gaps. There's more and more numbers which are not representable in that floating point system. And the next slide actually illustrates that on my system with a running program. This program prints out a value which is defined in limits.h, an integer value. What it is it is the unsigned long maximum. It's the maximum number you can get for an unsigned long. And on this system, it's 32 bits. And so this is 2 to the 32nd minus 1, 4 billion something there that you see. That's the actual number. Now, what I'm going to do is I'm going to store that into a float. And if you look down at the printf statement, I print out x as the first floating point number. And look what I get. I get a number which is not equal to the number that I expected it to be. There was some error in storing that into a float. And that's because the float system is not as dense as the others. It has less precision. Therefore, this particular number, 4,000,000 something 295, falls into one of those gaps. And so it becomes the closest number which is actually in the floating point system. So that's interesting. However, if I increase the precision, as you'll see as I did with double and long double, well, there's no problem there. Y and Z do have the correct value. So just an interesting feature that some people don't think about. When you use floating point numbers, sometimes those numbers just aren't there. Literals are just a way of hard-coding constants in your program, and they're usually used to initialize variables. Any variable ultimately gets initialized by a literal, whether it's in a program or through reading some value somewhere else. And then other variables will be just combinations or computations from those. The first bullet shows you how to initialize ints with literals. When you use just a regular old integer literal like 9, that's interpreted as base 10. There are 2 exceptions to this, and one is illustrated in the initialization of the variable j. If you begin with a 0, which of course is normally redundant in initializing integers, in C of course it is not, what you get is base 8. So 017 is 017 base 8, which is, what is that in base 10? That's 8 plus 7 is 15, so that's really the number 15 in base 10. And then you can also do hexadecimal. So here k is being initialized with the hexadecimal value 7f. Now these are all legal C statements the way I've written them, and so notice that I have a comma in between each declaration. So you can declare and optionally initialize a number of variables in the same statement. The next line shows you how to do characters. You use a single quote with a single character in the middle, and that will initialize that character variable. Now keep in mind that characters are just integers. If you wanted to, you could also store into a character variable the actual encoding, the number which represents that character. Now that's not a good idea, of course, because by nature that's not portable. It assumes that you know the encoding that you're using. What I've done here for this example is just to show you that for ASCII, You could type in 97, and it turns out the C2 and C are the same. If you were to print them out, you get the same value. So C equals quote A quote is the same as storing a 97 in C, because that is the ASCII encoding for a lowercase a 97. This usage of numbers with character variables, though, is pretty uncommon and actually not recommended. You're not going to get any errors, but it's just kind of a style and readability issue. If it's going to be a character, use characters, not numbers. If you want to specify that a literal integer is a long, then you use a suffix, and you use an L. You can use a lowercase l if you want, but I find that confusing because you can't really distinguish that easily from the numeral 1, so I use the uppercase L. Let's see, what's next? Float. It turns out that when you type, well, skip down to double. As you can see, when you type in a floating point literal, like 2.3, it turns out it's double by default. In other words, double precision is the default precision in C. You get better than float. If you want to conserve space and resources and use a less precise floating point number, then you have to say so. You have to give it an F suffix, which I've done in the declaration of X. Long double is similar to long for integer. What it is you make sure that you have a decimal point in your number, and then you, in addition, use a suffix of L. And that tells the system that this is a long double literal. And then finally, there is a way of initializing strings. Now, I realize we haven't talked about these, and we're not going to talk about them until Chapter 5. But I just wanted to be complete here and show you that there's one more type of literal, and that is where you use double quotes. And you can store that into an array of characters, and it automatically takes care of that for you. It puts H into the first position, E into the second, etc. But we'll talk more about that later. In the previous chapter, you saw the use of the \n to insert a new line. And as I mentioned, that's called an escape sequence. Well, there's a lot of escape sequences. These are, of course, just special character literals. And here they are, the ones that you can use in C. This is most of them. I've actually left a couple off because they don't exist in Java. So these are the ones that will work in both languages. \T is a tab, and that, of course, is dependent on what your system uses for tabs, but usually they're 8 characters. \0 is a null byte. That is, it's actually an encoding of 0 stored as characters, but it'll be all zeros as far as its bits. We'll see more of that later. That's important with string processing. If you actually want to have a / come out, well, you have to have a way to do that. You can't just say / because, as you can see, / is special. It introduces an escape sequence. So to get a single /, you just put down 2 of them. Let's see, \b is backspace, \r carriage return, \f is form feed. They're not used all that much, but they're there in case you need them. And then finally, you can define any character knowing the encoding by the octal bit pattern. You say \, and then give it 3 digits. The first one could or doesn't have to be a 0, but probably will be. But it's interpreted as octal, whether you have a leading 0 or not. And again, though, this is only if you know the underlying encoding system. Most of the time, the ones that you use will be the first 4. A constant in a program is something that cannot change, a variable that cannot be modified. And those are important. Sometimes you actually want to have some value in your program and give it a name, a symbolic name. And yet you don't want it to change, and you would like the compiler to enforce that. You don't want to accidentally change it and not know about that. Well, you can do that in C with a special keyword which you use as a prefix to your declaration. It's called const, short for constant, of course. The best way to interpret that would be read-only. You'll see why that's important later, but just think of const as read-only. And so the way that we would initialize such a variable is in the next bullet there. For example, const int I equals 7. Now, it's important that what you initialize a const with is itself constant. And so you commonly use a literal. Or you could use another constant which has previously been defined. So you have to initialize the const in its declaration because you can't change it later. The compiler won't let you. One crucial difference between C and C++ as far as const variables go is that you cannot use them as array dimensions in C, but you can in C++. I know it sounds strange. It's just one of those things that happened for historical reasons, but they did fix that in C++. Well, if you can't use const integers as array dimensions in C, then what's a good way of doing array dimensions? Of course, you can always hard code them, but that's not considered good practice. Most important constants and other concepts in a program should have a name. Well, that leads us to another pre-processing directive, which we'll talk about. That's #define. Let me just say right now that this directive, as important as it is in C, is less important in C++. But for the purposes of being able to do arrays in C in a reasonable manner, we're going to talk about it. What the define directive does, again, it's a preprocessor directive, so remember, it takes place before the actual translation of your code into object code. Basically, during preprocessing, the compiler is going to look for any occurrence of the symbol that you want to define, and it will replace it with text according to the define directive that you have given. As an example, look at the last bullet. I have #define space size, and again, here's a reminder that we have a convention that constants are uppercase in C, and then followed by a space and then the actual value that I want it to have. So if the preprocessor sees during preprocessing a statement such as int a sub size, and that's an array declaration. Again, we haven't talked about arrays, but I'm assuming you know what they are. Well, the preprocessor will actually make a substitution there. It will substitute the text size with the text 100. I'm talking text here. There's no other smarts going on there. This is strictly text replacement. So it's as if I typed int a bracket 100 bracket instead of size for the dimension. There are two basic types of arithmetic in computing. One is integer arithmetic and the other is real or floating point. We've already seen an example of this. With floating point, you keep the decimal portion. With integer arithmetic, you don't. So for example, if I declare a couple of integers and divide them, I'm going to lose their fractional part. In this example, I've got I is 2 and j is 3. When I try to initialize k with I divided by j, well, that's 2 divided by 3, and that's going to be 0, because 2/3 is a fractional part and it gets dropped. So when you want to keep decimal parts, you have to use floating point arithmetic instead. But the big problem there, that you at least have to be aware of, is round-off error. In other words, the number that is computed may not exist in your floating point system. It falls into one of those gaps that we talked about earlier. So you got to be careful, and we're not going to say much more about that here, except for which number in the floating point number system it chooses as the closest, or whichever one it decides to come out as, really depends on your platform. For example, if you do some floating point calculation which falls in a gap, it can go left or it can go right. What's it going to do? Is it going to round and go to the closest one? Is it always going to go to the right? Is it always going to go to the left? That depends on your platform, and you can actually look that up in your documentation. We've already talked about the fact that there are different flavors of integers. As a matter of fact, if you think about it, there's 4 at least. There's character or char, short, int, and long. But there are not 4 different flavors of integer arithmetic. There's only 2. And as a matter of fact, depending on your platform, there might only be 1. There's only int and long arithmetic. For example, if you took a short and you wanted to add that to an int, well, if there are different sizes on your platform, that's going to be a problem. So what the compiler will do is it will widen the short or temporarily convert it to an int, which is not a problem, of course, because no information is lost, and then it does the operation. So basically the way things work is that if your operands are not the same size, the smaller one will be temporarily converted to the larger one so that they match, and it has to be either an int or long. So again, if you took a char and tried to add it to a short, you can do that, but both of them will be converted to an int because there's no such thing as char arithmetic or short arithmetic. It's either int or long. Now, it's also possible for you to lose information. Of course, you need to be careful. For example, if you were to take a long and store it into a short, well, you're going to lose some information. If the value that you have in your long variable is small enough that it can be represented as a short, well, then you don't have any problems. But if it's not, then you have no idea what's going to happen. That behavior is unspecified by the standard. It's actually considered bad news, and so you shouldn't do it. So you need to be careful and watch out for narrowing conversions. Speaking of narrowing conversions, compilers are pretty good at letting you know that there could be a problem. Many compilers will give you a warning when you want to, say, store a long into an int or a float into an int, something like that. But sometimes you want to do it, and you want the compiler just to leave you alone. You want to say, hey, I know what I'm doing, let me do it. Well, there is a way to do that, and that is what we call a cast. A cast is just a way of explicitly converting one type to another, and the compiler will leave you alone. But of course, you need to know what you're doing. The syntax for a cast is pretty simple. You just put the type that you want to go to in parentheses before the value that you're converting. So in this example here, I'm saying int I equals int cast on x. Well, I'm assuming here that, say, x is a floating point number. Well, if you left that int off, a good compiler would give you a warning message that you may lose some precision. By putting the cast there, I'm telling the compiler I know what I'm doing. You're also advertising what you're doing to the reader. To put in a cast when you're using it is a good thing, when you actually want to make such a conversion, because it kind of jumps out at the reader. Ooh, here's the cast. Let me just qualify that statement I just made. And say casts can be troublesome, and you only want to use them when you absolutely have to. When we get into C++, we'll see a little bit more about that. Now, casts are commonly used when you want to force a particular type of arithmetic. So, for example, if I have two integers and I want to divide them and keep the floating point part, well, I need to somehow convert one or the other to a floating point number. That is sufficient to force floating point arithmetic. So here I have I and j, and they're both integers. By putting a float cast on either one of those integers, that's enough to let the compiler know that for the purposes of this operation, I should be converted to a float. Of course, that will in turn cause j to be converted to a float because, as we said earlier, both sides are balanced. And then the floating point arithmetic will be done, and you will not lose any of the fractional part. So to summarize what we've talked about in this chapter, built-in C data types are numeric. They're either integer or floating point, and that's even characters. Integer arithmetic truncates fractions, so you got to be careful there. Whenever you want to preserve your fractions in arithmetic, then you need to force floating point arithmetic to keep that. However, if you do a lot of mathematical calculations, you can be hit by round-off error because floating point arithmetic can be inexact. In other words, you calculate a number, and lo and behold, it's not in your floating point number system. You've got a little bit of error. It may not seem like a lot of error because that gap between two numbers is hopefully pretty small most of the time in your floating point number system. But you need to keep in mind that a little bit of error here, a little bit of error there, in chained calculations, in a big sequence of calculations, can add up to a lot of error. Again, there's a whole science that deals with that, and that's definitely outside the scope of this course. When you have two values that are being combined in an operation, they will always be balanced. That is, one will be widened to match the other. And in particular, with integers, there's only two types of arithmetic, int and long. You don't have arithmetic for the smaller sizes. If you want to force a particular type of arithmetic, you don't have to declare temporary variables of the type that you want, like we did in the average program, for example, in the last chapter. You can explicitly cast a value to a certain type, and that's enough to force the type of arithmetic that you're after. Just to get used to numeric types and numeric operations, what I'd like you to do in this exercise is just read a number in from the keyboard. Make sure it's a floating point number that has a decimal point. So, of course, you'll have to use the %F format in your scan statement. And round it to the nearest integer. Print out the original number and the rounded result. I'm assuming you know how to round something to the nearest integer. If you've forgotten, well, it's in the solution.